last discussions, which is the polar double integrals. So we are going to have a final exam. The schedule, I think we have on Thursday, June 6th. Is that okay? Or do you want earlier, Tuesday or Thursday? Well, it's up to you. You can think from other course schedule if you know the schedule already. For example, your chemistry and physics, maybe when is the schedule? But for my calculus, I think it can be between 4 or 6. 4 or 6. So Tuesday or Thursday. Okay. So let me continue a little bit and perhaps finishing off some examples here just to make sure that we are on the same page with the textbook. So Thursday, 6th June, is that okay? I will ask again maybe next class. Okay, I will ask in the Google form to let you know your choices. Okay, so the idea for the double integral, if we take a little bit review. Okay, so basically the idea is if we could see the area of the double integral, which we are going to integrate it, if the area, for example, this we name it D, if that is a polar curve like this, a circle, or any other polar curve, it could be any other polar curve. Basically, we can make it into, for example, this part here, from the Cartesian xy, we can convert them into a polar using this conversion to polar. And when we doing that, when we are converting the Cartesians to polar, we are also converting the integrations variables, which means we need to include this r, and then the r dθ. This multiplication with r is very important because this is frequently missed out. Okay. And we could see later on, I think near the end of the chapter, we can see some other proof how we can get this r and how to make it or how to confirm it that this is true, that this should be having a radius. We have seen that from our interpretations in Riemann definitions for the double integral in polar, we could see that this r should have been there from the approximations. Okay. But later, when we learn about the Jacobian, when we transform a functions to another some set of axes, so-called axes, we need to multiply with what we call this is a Jacobian transformations, and the result for that is actually this r. Okay? We are going to learn that, but I think after a few topics. Okay? So we convert all this, and basically, after you convert, the way you solve the integration is the same as you did in calculus 1. So basically, if you have the squared, you can change to the double angle formulations to reduce the formula or to add the formula. And then whenever you see any identity in the trigonometry, you can substitute and then solve. Okay. And I hope you can do it regularly. Okay. If you have some difficulty here, we don't have much time to conclude that, to explain that, okay. Because I think few weeks ago, or perhaps in the middle of the courses, there are some complaints and maybe some suggestions that I need to explain step by step. But I cannot do that because this is supposed to be in calculus 1. Okay. So that is the example. So if we have another example here, perhaps the example 3, I will leave that for you. I will get into this example 2 for a while. So we have a double integral that we are going to integrate this with respect to y and then with respect to x, which means this y is for this the inside integrations, which is from 0 to square root of 1 minus x squared. And dx is for negative 1 to 1. Okay? So we can start writing the region, okay? The region that we want to evaluate. Or even we can draw this region. So it says that x will be between negative 1 and 1, and y is between 0 and square root of 1 minus x squared. And of course, if you're looking at these equations and you want to make it like directly following this dx dy or dy dx structure, well, perhaps we can do directly take the integrations. Okay? But in this, because we are in the polar topics, because if we look at the description here, and if we look at this y and the square root of 1 minus x squared, we can see that this is actually a semicircle. Okay? If you can see that. This is just a x squared plus y squared equal 1, the circle. But we take half only the top, only the positive one. Okay? So we can think about the x squared plus y squared equal 1. Okay? And from here, we can write this, and we could make it into this. And don't forget plus minus. I think some students always forget that we have two positive and negative, especially the last quiz. I observe some students take it this positive, so then they are only getting the positive critical points. So it should be 4 critical points, and they are getting 2. And they are just writing 1 and 2. Okay? So don't forget, every time we take the square, there will be plus and minus. Okay? But here, in this questions, in the example, it's only positive. So if you have a circle, you only take the positive part. So if we take here as a circle, and let me just describe a circle here. Right. Okay. Okay. Let's say this is a circle, x squared plus y squared equal 1. And because we established y is this, and x is over there, that means y will be positive here. So actually the region here will be from x negative 1 to 1, from y equals 0 to this. Okay? So this means this will be the region. So this is the R. So let's say this is the R. So we can transform this into a new R, which is converting the x and y based on this. So this is a radius 1, right? And if we turn to polar, we start and imagine that this is angle 0, and then we are rotating until this side, which is pi. So its angle is from 0 to pi. Radius, because there is nothing hollow inside, we can assume the radius is going from 0 to 1, and then rotate. Remember, every time you have the polar, you need to rotate the region. Okay? Rotate from this axis, and then rotate. Okay? So we write the polar r theta as the 0 to pi and 0 to 1 for the radius. Okay. So then we can write this, and we can convert, remember, x with r cosine theta, y with r sine theta. And since this is x squared and y squared, then when we plus this, this is r squared, right? This is r squared. So this becomes r squared, and don't forget to multiply with another r, and then the r d theta, and then plug in the endpoints, which is, this is 0, pi, and then 0, 1. Now we can write, let me write down here. So this becomes r cubed dr d theta. And now we have all the endpoints are in constant, which means if it is constant, we can separate the integrations. We can split theta with the angle, with other theta, and r with r. Okay? So we can split, and it makes much simpler case. So we can make it this and that. We can do this. So this becomes only theta and becomes pi when you plug in, and this will be, or we could just take this pi over 4. So from something that is, if you try to make out your way through the normal integrations, which is very tedious and maybe a little bit longer, if you convert to polar, you will have this simple calculations. So every time you see anything that can be turned into polar, and maybe it will be much more easier to convert, then that's probably your best way to solve it. Okay. Okay. So sometimes you are given this type of questions, which you need to assume. So it will not going to guide you use polar to solve this. You need to think. You need to think when you are using polar or and how to solve it. Okay. Another part of the questions is, if you have this example here, which you need to find the volume of the solid that is bound by the plane z equals 0, and you have, here we call it paraboloid 1 minus x squared minus y squared. There are several ways to approach, but I think the first way, if you know how to draw the paraboloid, you can draw. I think it's not too complicated. Paraboloid means it has a lot of parabola. If you view from the sides and from the sides, and you make maybe, if x is 0, this will be 1 minus y squared. It has a parabola. If you check zy axis, you see from that angle. And if you see it from zx angle, it will be also a parabola. And if you have the, perhaps when z is equal to 0, then you can see that if we solve and simplify, it will be a circle. It will be a circle. So it is a circle, and then if you look at the xy, it is a circle. If you look from the side, it's a parabola, and the other side also a parabola. So I think based on the information given, which is the z equals 0, we can take the 0 inside here to get the intersection. So this is paraboloid, and then we have a plane here. And it will make a circle. Okay? So we can have the intersection when z equals 0, so x squared plus y squared equals 1. So the intersection is a circle. Well, if you want to draw, we can draw like in 3D. But I think if you want to draw in the circle alone is also okay. So this is z, let's say this is x, and this is y. And suppose this is the circle. Let me make it. Okay, that's the circle. And the paraboloid means we have here maybe this one for zx and this one for zy. So it's like this cube, like a dome, or perhaps if you know the tools for making juice for orange, it's like that. If it's juice. Okay, so anyway, this is the paraboloid. So this is paraboloid. So then if we take this volume between the plane and the paraboloid, so we can just write this with, let's say, D, this is the projections, the circle. And let's say this is the paraboloid. Let me just make up this as dA. So if we know this, and we know that the projection is a circle, which is a polar, and the full circle means that it will be 0 to 2 pi, and then the radius we know it's equal 1. So we can assume that it's also from 0 to 1. So we can write this as a polar directly. So this will be the angle, this will be the radius, and all the x and y we can convert into polar, which is basically this is r squared, right? So this is basically x squared plus y squared, which is r. So we can write this as 1 minus r squared, and then r dr d theta. And then the same way we did from the previous example, since this is a constant for both endpoints, we can separate and then integrate each integrations. So you can do this, I think, by yourself, right? But the answer should be pi over 2. Okay. If you want to use the dx dy, you can do that, but I think the problems will be in the endpoints, because it's a full circle. Then for y we'll be having the square root for both endpoints, and it adds some complexity. Okay. Okay. I hope this is the integrations. My expectation is very simple, and you should be able to do it. Okay. All right. Now, next one, the last part on the polar is if we have any polar curve aside from the circle. Let's say we have this kind of h of theta. So we have a functions in polar forms. We can write this basically the same. What we did is actually the endpoint is not the radius anymore, but the radius in terms of polar functions. Remember the polar functions, we start always with the r. Remember that we write r equal function of theta, right? So basically this is telling you that this is a function. So the problem when you have this function and this is a constant, then you cannot separate or taking the Fibini or the Clairaut's or the Fibini theorem by switching the orders, okay, or separate the variable. So you need to do from the inside compute and then take the outside integration. So you need to do step by step. Okay. So for example here, I think we have example here. Oh, we have here. So example 4 here. So suppose that we have this Rose curve. Okay. So this is from your chapter 10 in the polar curves. I hope you still remember. So find the area enclosed by one loop. So one loop means in the Rose curve for cosine 2 theta, we have 4 leaves. Okay. Remember that if we have the even number for the Rose curve, for example, if we have cosine 4 theta, it means the leaves will be 8. And I hope you can know how to draw, but I believe you'll be confused about that. So I think I will provide the picture whenever we get these questions. Okay. So the question is asking the area here. Okay. So first is we need to make sure what will be the endpoints, right? What will be the endpoints? And as you can see from the figure, it is started from negative pi over 4 until pi over 4. That is for the theta. Okay, and I don't think I have time to explain why this is pi over 4. Okay, pi over 4 because when you plug into cosine, it will be 0. Right? So it's going back to the original positions. So we can write the D. And since there is no other polar curves, so only one functions, right? Only r equal cosine theta. So we can write D, and we can explain the endpoints. So the theta is from negative pi over 4 and then for the r, if there is no other information, we can have the other part of the function will be 0 up until this cosine 2 theta. Okay. So practically it's saying that the r is based on from this 0 and then this curve. Okay. This curve. Okay. So we could write the area. If you remember, to find the area in the double integral is basically we double integrate the dA. So the functions will be equal to 1. Okay? So when the function equal 1, it means that it is actually compute the area. Okay? So this will be equal to, so dA will be r dr d theta. So there is no specific function that need to be computed. So it will be just changing dA to r dr d theta and then put all this information for theta and for the r, 0 and cosine theta. So first we need to deal with this inside integrations, r dr. So this will be half r squared and then pull in 0 and cosine 2 theta. And then we can evaluate, and this will be cosine squared 2 theta d theta. And remember, whenever you have squared either sine or cosine, take the double angle. So when you have 2 theta, you have the double angle becomes 4, right? Become 4. So we can have a cosine 4 theta will be 2 cosine squared 2 theta minus 1, right? So if we divide by 4, it will be half, and this will be 1 over 4. So half is 1 over 4 plus cos 4 theta over 4. So we can change into this 1 over 4, and I will make out this 1 over 4 here. And then this will be 1 plus cosine 4 theta d theta, right? And then let's complete this. It's become 1 over 4 theta plus sine 4 theta and then divide by 4. And then take the pi over 4. And then if you get this, then you can perform in the calculators. You can always perform in calculators if you have the constant here. For example, from here, you can perform in calculators. But to avoid mistake, then I think there will be some mistakes, and also to avoid some algorithm mistake that might happen in your calculator, I suggest you get the calculators maybe here or here to make sure that it's safe to copy. Because when you type the brackets, maybe you miss out one bracket and then it mess up the calculation. So take that, and you can set your calculators to be in pi fractions, right? So that the result will be much more clear. Instead of the decimals, I prefer to look at this pi results. Okay, one more example. Let me copy first. I expect to write here, but let me copy, cut, and then write here. So another example. So this is another example that is it's quite difficult to visualize. So the graph now is pretty much need efforts to draw. Okay, if you could see the next questions while okay. So next question, find the volume. We have two different surfaces. The first one is paraboloid, z equal x squared plus y squared. Okay. Which you can see that if z is a constant, which means that it will be in every part of z, we can always slice the circle equation, right? The parabola. So the parabola is going to have in xy projection is always a circle, right? And then we have what we call the cylinder. And I think to help to get this perhaps into a form that is easy to understand, we can take the what we call the standard form for the circle. So if we take a so perhaps we need to add, this is 1, so this is 1, so we have x minus 1 squared plus y squared equal 1. So this is something that we have on the left here. Okay. So I think it's much more easy to see that this is a circle. The center will be 1, 0. So 1, 0 is here. So your circle is here with radius 1. Okay. Radius 1. Okay. And if you remember what this is about, this is 0 to 2. And in polar, if we remember, when you have circle on the right, so you have either left or right, this will be cosine. If you have on the left, it will be negative cosine. If you have on the top here, it will be sine. If you have here on the bottom here, it will be negative sine. Okay, I hope you still remember that. Okay, but anyway, since we have 2 in this part of x, so we know that the point from the original point to the last point here 2, which means that the circle is cosine theta multiplied by 2. Okay, that's the polar for this equations. And then this is the cylinder, which is we see from the top. So it's actually a tube. Okay. So if we look at the side, this tube. Okay. And it will intersect with the parabola from here. Okay. So if you slice this parabola, you will see from the side is the x squared, z equal x squared. From the other side will be z equal y squared. And from the top is the circle. So you have the big circle which center at the 0, 0, and you have this green circle which center at 1, 0. Okay. So then, what will be the questions? The volume under the parabola, so this paraboloid, and then inside the cylinder, which means that this one here, that is sliced by the parabola. This is difficult to see, but this is going to be our volume, which actually we could compute that as well. We can write up the conditions first. And since we are going to focus more on the cylinder, because it's going to be inside the cylinder, so it will be rotate throughout the circle in the cylinder. So from the let me write here. From the disk here, we can write the region D. That is going to be negative pi over 2 less equal theta less equal pi over 2, and then the r will be 0 to r to 2 cosine theta. Now we take that into our volume. We can write up the paraboloid. So volume will be described. So we let this function x squared plus y squared, that is our surface, and then the A. Okay. And then we are going to convert this. So this will be r squared, r d theta. This will be negative pi over 2, and 0, and then 2 cosine theta. And then start slowly solve the inside of integrations. We will have 1 over 4 r with power of 4, and then maybe let me write with different color. And plug in all of this, and then we still have the theta to be computed. And we put in the 2 cosine theta, so this will be should be 16, but divided by 4 becomes 4. I will write outside. And then the r power of 4 becomes this cosine power of 4 theta d theta. And then, since this is a full circle, so we can make exchange by taking this multiplied by 2, and then taking this from 0 to pi over 2. Okay, we can write do to symmetry. Well, actually, you can do this at the beginning. Well, you can do like twice of 0 pi over 2. Okay, you can do this at the beginning. But anyway, we can compute this. And then what should we do? We can let this, sometimes we have this kind of solutions. For example, we can think this as a cosine squared theta and then squared. Okay. We can start from here. Take this to double angle and then take the square, and you have some expansions, and then you need to take another double angle. Okay. So we take that. So we have here is the 1 plus cosine 2 theta over 2. So that will be making out these formulations. 1 plus cosine 2 theta over 2, and then take the squared, right? And then d theta. And then we solve this for, we simplify and solve. And I think we can take out 1 over 2 out. So 1 over 2 squared, we can take out, will be 1 over 4. So 1 over 4 and 8 becomes 2. And this will be 1 plus 2 cosine 2 theta plus cosine squared 2 theta. Okay. And then this cosine squared, we have another double angle to make it 4 theta. Okay, to make it 4 theta. So this will be 2. 1 plus 2 cosine 2 theta plus 1 plus cosine 4 theta divided by 2. And then d theta. Okay. And anyway, after you get this, I think it will be easy to be integrated. This should be just sine and then divide by 2. This is also sine 4 theta divided by 4 and then multiply with half. So you imply it and calculate compute. Should be equal to 3 over 2 pi. Okay. And that's it, the polar. I have several exercises prepared for you, but I think for the exercise, I will have on the Thursday class. Okay, so I will have and perhaps on your TA class you can have also some practice. Especially, I think you need to really catch up your algebra. Okay, your algebra. Okay. Okay, so that's the double integrals in polar coordinates or in the polar curves using polar. Okay, any questions? Okay, so that is the double integral in polar. Okay, the next part in our course, in our class, we are going to skip the applications, which is the moments, the inertia, and the center of mass. We are going to skip all that, and we move to the surface area. Okay, we move to surface area. If you look at the textbook, that is on 15.5, so surface area. So we are going to move on. Okay, we skip this. This is some exercise that perhaps we could do perhaps next Thursday, and maybe your TA will also have exercise later on. Maybe exercise from the previous part. the double integrals. Okay, so surface area. What is the expectation, or what is our goal in this surface area? So what we are going to get is, if we have a functions, okay, suppose that this is a surface. So suppose that this is a surface. Suppose that this is a surface Z equal a, suppose two variables, function of two variables x, y. And suppose that the S is a surface with this equation. Okay, so F or S is surface with Z equal F x, y equations, and F is defined and partially continue or partially derived, can be partially derived. Okay, and then assume, for simplicity, for the arguments, that this function will be a positive functions, and the domain is rectangle. Okay, we will continue later on. Okay. Yeah, for the surface area. Okay, so assume this is going to be a domain is rectangle. So we can also write, based on the picture here, that we have this some sort of small pieces, okay, small pieces that is projecting to the rectangle domain, which in the surface part, that will be our tangent plane. So this will be a tangent plane here. So let me write, this is tangent plane. So in other words, we could also write the tangent plane S to the point Pij, that is the point that we observe, is we call approximately or approximation to the S near the point. Okay, near the point. Okay, remember that if we have the points around the observing points of the tangent plane, we can do linearizations, right? And then the delta t, which is the part of the tangent plane, okay, and we can write this delta t as a parallelogram. It lies directly above the rectangle on the xy, which is the small r, rij. Okay. This delta t is actually approximation to total area of the S. Okay, so if we cut into small pieces, like a very, very small, for this delta t, and we combine all the delta, this will be the surface itself, the area of the surface. Okay. So then we need to define this parallelogram, okay, this delta t, in terms of this with the vectors a and b, So we can write for now, we can write that the area of the surface will be, we take the limit, and taking for both of the x and y, which is on the delta t. So we have so for a while we have these definitions, and this definition holds for the approximation. The approximation from the tangent plane, and then we can write the tangent plane as in the delta t. And now we focus on these vectors a and b, which is described from the point P. Suppose we have point P, which has these vectors comes out. We call this as a and b. So then we can maybe let this a and b vectors from point Pij, and both vectors lies along the sides of the delta t, as you can see from the picture. And then we can also relate the area for the delta t for it is the area of parallelogram, which we can write as the cross product, or the magnitude of the cross product A cross B. And then if you remember, in the tangent plane, we have partial x and partial y, right, as our tangent slope. So that tangent slope we can also define. So if we have a partial f, as we defined from the beginning, we have partially derived for f. So we have the partial x at certain points, let's say xi, yi, and then we have partial y. These two equations will be the slopes of the tangent of both tangent lines through the Pij in direction parallel with A and B. Okay. So, if we could see this, that the projection is having the delta y for this y here, and a small delta x. So we can write the vectors A as delta xi plus partial x at xi yi point multiplied with the delta x k. And this, with the same reasons, this vector b, which means this, so we need to describe that this vector a and b will relate to the positions in which that for the x-axis it will be on the delta x, and for the z-axis it will be partial x dx, partial x dx. And with the same reasonings, we can also write b is having delta y in j and plus partial y delta y k. Okay, so we have the vectors. Then we can compute the area, which is we need to compute the parallelogram. So the delta Dij will be a parallelogram area, which is A cross B, and then we can compute the magnitude value. So we can compute A cross B first, and I hope everyone can follow the cross product, okay, hopefully. Have you learned also in physics for the cross product? Or no? Statics? Okay. So cross product, for the vectors, we can write the axis or the unit, and then the equations, which is we have delta x, this is A, and J is 0, and this will be oh really? And this is partial x. Let me write xi yi delta x. This will be 0 for the b, and this will be partial y, and then delta y. Okay, so then the result, so we could do the determinant, we call this a 3x3 determinant in matrix. Anyone still not familiar with matrix? Or perhaps doesn't really know what that is? So, but anyway, I hope you can catch up. Okay, you can catch up. So we can take this a minus, let me use different color. So minus partial x, and then delta y, because 0 minus that, and then this should be the I, and then minus, another minus, right? For the second part is partial y, and this is delta y delta x, but I will write delta x delta y instead, and j, and then for k it will be plus dx dy. Okay, so that's the A cross B, and then take the magnitude value of A cross B. Then we could square root of all of this, and then take the squared inside, or let me make simplified, okay? Because all the equations, they have the delta x delta y. I will move delta x delta y outside, so I will factor out that scalar. So we have negative partial x and then plus, oh, I forgot the j. So I, j, and 1k, or k. And this will be, suppose the delta x, delta y is delta a. I'll write this is as a delta a, which much more smaller equations. So this will be
partial x of the xi squared. And I will remove this negative because we have squared now. And plus 1, and then this will be delta A. And that will be the area of the parallelogram. And then from the definitions, we have this limit. Then we can exchange this delta t with this square root. Okay, so we can write the area becomes limit m and getting infinity and taking double sum, and then maybe let me just copy. I'm too lazy to write this. And we have this, which we can use the definition for the double integral. And taking this as the definitions. So if you have the surface z, which is function of two variables x, y, and then we have the continuous partial derivative, partial x, partial y, the surface area will be double integrals d. D can be dy dx, dx dy, or it can be also a polar, but let's just write d. And this will be partial x squared, partial y squared plus 1 dx. Which means every time you are big X to find the surface area, you need to find the partial x, partial y, put down that information into this part, and then solve the double integral. How to solve double integrals? We can have, if you remember the previous part, we can maybe switch the order, dx dy, dy dx, and perhaps we can convert to polar. So this is also part of solution. Okay. Okay. So that's the surface area. And if you notice the similarity of this double integrations in surface with the arc length, when you learn the arc length formula, it's pretty similar. You have the square root and then 1 plus either dx dy or dy dx squared, and then you get the dx or dy on the other sides. Okay, maybe a couple examples. And pretty much the surface area is like a short notes just by taking these equations to compute the surface. You will see again this kind of equation, the surface area equations, maybe in the engineering of mathematics, when we learn about the surface integrals. But that will be for the factor calculus part, not in our topics. Okay, now just a quick example here. I have two quick examples. So example 1, find the surface area. Z equal x squared plus 2y plus 2 lies above this T, region T. Okay, so every time you have this kind of questions that you are specifically having some points or maybe having some equations on the region, sometimes we need to describe first whether it is the endpoints will be a constant or perhaps another equation that we need to solve. So we need to draw this triangle. Okay, so draw the triangle. Since all is positive, so I will start with 0, 0 here, and then 1, 0 perhaps here, and this is another 1, and this will be 1, 1. So I will have this line and also this line here. So this is our t. As you can see, that if we would like to describe the endpoints in x and y, we could describe this, if you remember, when we learned the double integrals a few weeks ago, or perhaps a couple of weeks ago, because we have this line here, which is we can have a linear equation. Then we can have two choices. We could make y as a constant, or we could make x as a constant, and the other one would be based on this line, right? And this line is because everything will be the same, so this is just y equal x. The slope is just 1. We can write this is a y equal x. And for example, if we take x from 0 to 1, okay, and then how about y? Y we could take from 0 to x. Okay. If we take y from 0 to 1, what will be for x? So if y is from 0 to 1, what will be for x? If you get it wrong, you'll be in trouble, okay? Your final exam must have that kind of question. Must. So it must be there. If you can figure out which one, then you are doomed. You are digging your own grave. Okay, so from where to where? So x is from? Anyone? Just give the points. From? If you miss out, there is still possibility. You could make this triangle. Okay? Make sure that your triangle is this one. So x is from? You can pinpoint the constant for x. The constant is here, right? Okay? So that must be the right side. So the x should be from this to this, right? Agree? So this will be y to 1. Okay? So you can choose. Okay? You can go for this or this one. And sometimes both will be having the same complexity, so you can just choose which one. Okay? So now we could express with these two possibility, and then we have the f. Let's say the z is equal of function of xy, and this will be equal to that equation. And this we can try to find the partial x first, which is 2x, find partial y, which is 2, and then put all this into the equations. So we have equations, and then let's just write this is t, and then plug in the partials. So 2x squared plus 2 squared plus 1, and still inside the square root, and then the a. Okay. So we have 4x squared plus 4 plus 1, or plus 5, right? So perhaps if we would like to see from 0 to 1 for x, let's say this is 0, 1, and then 0x, and then this will be 4x squared plus 5. So this is dy dx. I think this is much easier. Okay, compare if you start from dx dy, which you can see some complexity there. So if we start from dx dy, I don't think you get the answer directly, right? Because this has this square root. And yeah, I think you need to have another x outside, or single linear x, right, to make it substitution. But here we can take this y and then we are getting the x, and we can use substitutions method. Right? So let me just give some review here. So we could take this. Let's say we try to integrate this. This will be y. Multiply with that, and don't forget to get the 0x, or let me write this with the black, and then we still have the x, and plug in x to y. So we have x, and then we have 4x squared plus 5, and all the methods in the integration you should be familiarized with it. So this should be taking du, 4x squared plus 5. So du will be 8x dx. So you will have a 1 over 8, right? You have 1 over 8. So you have 1 over 8 integrations, and then you have u with power of half du. And if you want to change all into u, then the endpoints also need to be changed. But if you are like me, that you prefer just to integrate u and then later convert back to x, I think that will be also very possible. And I'm usually doing that, because if we convert to u, then we are going to take the u is basically from 5 to 9, right? So we can take this 5 to 9 and compute, or we compute the u with power of half, and then saying that this will be, because it will be 2 over 3, and this will be 3 over 2, right? And I will put back the 4x squared and then plus 5. And then I will just take this 0, 1, 0, 1, and then this will be your answer. Okay. So it could be using this of 1 over 8. I forgot 1 over 8. Okay, this is for your own calculation. Okay. You could do all substitutions, the whole thing, making this into u, including the endpoints. Okay, don't forget that. Or you do the integrations just to make sure that you can integrate this, pull out this 2 over 3 and 3 over 2, and change back the u into x. And multiply with 1 over 8, don't forget. So this is basically the same, but this is going to be 0 to 1. I prefer this because I'm looking for the 0, 1. But if you check this, it's also okay, I think, because this will end up with the same structure eventually. So this one will be 1 over 8, 2 over 3, and then 3 over 2 from 5 to 9. And you will see that what 5 and 9, it could be from this 4 or 5. So this will be the same thing. So both will be about, because we have the square root, or 3 over 2. So this will be a little bit not full or full whole numbers. This will be 27 minus 5 squared of 5. Both will resulting in this equations. Well, in the exam, if you are prefer to use calculators, and maybe the results will be in decimals. I think some calculators, if you put some adjustment, it can give you the square root forms. But I don't think all calculators are available. You need to set up the settings. Okay. So as I mentioned, I think at the early beginning of our class, that the last part of the content in the calculus 2, which is the partial derivative and the multiple integral, that will be the backbone, or the main content actually. The 11, 12, or 10, 11, 12, 13, They are, some of them are additional or support for 14 and 15. Especially 10 is just a support, and 12 and 13. 11 kind of like sidelines, not really in line with the calculus, but it's like a sidelines for the series, which we can get some correlation with calculus, because it goes into the, so every time we add, we have the sum, and sum can be defined in terms of the integration and so on. So I think that's the example. I have one more example here, but I will go through quickly. So this part, this last example here, is we have the paraboloid. I think same paraboloid with the previous example. It lies under the plane z equal 9. So we have the plane z equal 9 that cut out the paraboloid. And then we need to find out the surface part of the paraboloid when we cut at the z equal 9. So if we draw, so we want to find, for example, if this is the 3D system, so if this is the if this is the 3D system, and this one is D, and this is the paraboloid, and it will be cut here at z equal 9. So at z equal 9, we have D, a circle which is having the radius of 3. If we take this 9, this is a circle radius 3. Which means that every time you see curves that has a tendency to be apolar or even a circle, then perhaps we can change into polar to make it simplified. So first, we can let this as f. And then we can write down the partial x, partial y, and then take the surface. And then I will write this 1 plus 4x squared plus 4y squared, and then the a. Now D will be a circle. D will be a circle with the radius is 3, from 0 to 3, and the theta for the full circle 0 to 2 pi. And then we could apply that and change this xy becomes r. Okay, so we can write this. I think I don't have much space here, so I will erase this, okay, for a while. Let me take this, go here, and I will write the final part. This will be 4 plus 4r squared, r, dr, d theta, and then this will be 0, 3, and 0, 2 pi. I think the first part, and then this one here, for the r, we can compute using this substitution. Because we have r and then r squared, we can let this become u, this become 8r. So we can cancel out with r, so we have expected to have the same 1 over 8 with that equation. So this will be having the same structure with the previous one. So 1 over 8, 2 over 3, and then we have it 3 over 2. And then I think for the theta, you can compute directly. So this will be 2 pi, so 2 pi multiply the result from u. I leave this to you. Hopefully you can do that, especially in exam. Okay. Alright. Okay, done. Surface area. So next Thursday, I will evaluate, overview some parts in polars, and maybe some parts in the early W division. Especially how to how to write the endpoint, especially if you have a function, or even if you want to make a change in the order from dy dx to dx dy. Okay? And then the next 1 hour, one part of this will be the triple integral. So we have not only double but triple. This is a little bit different from last year. Last year, I moved until this part, and then Jacobian, and then finish. But this year, I've decided to introduce a triple, and Jacobian, and then final. It should be, you have like the last 2 years or 3 years, we complete all, including the triple integrals in the cylinder and the sphere coordinates. So it's like a 7 to 8 topics in the multiple. But now only the regular triple integrals and Jacobian line. Okay, so 2 more topics. Then 6th of June. 6th of June will be the final. And hopefully, I can give you another exercise and perhaps some example from maybe last year or maybe last 2 years, so that you can have some expectation what might be happening. Okay, I think that's it for today. Any questions?